Standard algebra is built to find a fixed value. You solve the equation, and you arrive at a single unmoving number. But a rigid number cannot describe the continuous, fluid motion of physical systems, like a crashing ocean wave. Describing the real world requires a shift in perspective, from finding a final destination to defining a rule of movement. This is a differential equation. It is a mathematical command that dictates exactly how a physical object or wave must behave over time. When the problem itself is a rule of continuous change, the solution cannot be expressed as a static numerical value. In calculus, taking a derivative is a forward process. We take a known shape, like this parabola, and extract its slope. Solving a differential equation is the reverse. Given only the rule of movement, we must reconstruct the original shape. If the rule is 2x, the reconstruction is x squared plus a constant, c. That constant represents missing information. Because c could be any value, the solution is an entire family of parallel curves obeying the same rule. You can differentiate any single curve in the stack, and you will always return to that same starting rule of 2x. A differential equation defines the behavior of a system, but by itself, it provides a list of potential candidates rather than a single unique solution. Predicting a physical event requires narrowing these infinite possibilities down to the one specific path an object is actually following. We achieve this by applying initial conditions, data points that describe the system at a specific moment. For example, we can specify that at time 0, our shape must pass through the coordinate 1. This condition mathematically forces c to equal 1. Every other candidate curve that fails to meet this requirement is eliminated. The differential equation provides the general rule of change, while the initial condition acts as the selector that identifies the specific shape. Combining these two elements collapses the family of possible functions into the single, predictable trajectory that models our physical world. The examples we have looked at are ordinary differential equations, which reconstruct change across a single variable, like time. However, physical phenomena like heat or sound waves exist across space and time simultaneously. A wave's height depends on both where you are and when you look at it. This requires a partial differential equation, a framework designed to track how a system evolves across multiple inputs at once. In this 3D model, the x and t inputs create a grid mapping values across every location as time moves forward. The solution to this multidimensional rule is a dynamic surface, defining how a shape ripples and flows through the physical environment. This result provides the state of every coordinate in the system throughout its entire history. The answer to a differential equation is the function that defines form, movement, and the resulting physical state of a system at every point.